As the title implies, higher order thinking can be rolled into unit monitoring for both gas treating and sulfur plants, and that is what this presentation is all about. We will be talking about a new technology that OGT has developed called ProBot and what it can do for you to help monitor your gas treating and sulfur recovery plants. My name is Simon Weiland, and I'll be the speaker presenting the material today. My colleague Nate Hatcher did all the legwork putting the material together, and I'd like to thank him for all the hard work that was put into it. I'd also like to take a moment to thank the SulGas Organizing Committee for the opportunity to present, and note that the conference is becoming a great technical resource to the industry. I'll just go over a very brief presentation outline for what we'll be covering in today's discussion. First, we'll try to answer the question I'm sure you're all asking yourselves: what is ProBot? I'll then go over what the motives were for OGT to even develop such a tool, and do a bit of show and tell to give a better idea for what's under the hood. I'll then transition into two demonstrations of the tool to show how it works and what kind of information you can expect to get out of it. The two demonstrations include a TGU debottlenecking project and a Claus reaction furnace temperature monitoring case. I'll then wrap up with how we plan to deploy this tool and some logistical challenges to be overcome. So the question you're asking yourselves, what is ProBot? ProBot is a technology spreadsheet with VBA functions and code that tie into the COM interface of both ProTreat and SulfurPro. COM stands for Component Object Model, and I've given a reference here for further reading if you feel so inclined to do so. Be warned, though, it is fairly deep reading and is not for the faint of heart. OGT uses COM as a communication mechanism between SulfurPro or ProTreat and ProBot, which is an Excel spreadsheet tool. The idea is to operate a virtual plant from within Excel, which has some benefits we will discuss further on. Given the recent introduction of COVID onto the world, remote monitoring of assets is becoming more and more important to do so. ProBot does much more than just monitor your assets. It provides some expert guidance in known problem areas of amine, sour water, and sulfur plants. What motivations would OGT have for creating such an elaborate Excel tool in the first place? Well, spreadsheets are the workhorse of every engineer. Virtually any calculation can be done. It is extremely easy to create graphs and tabulate and analyze data. It's easy to share and pass data amongst your colleagues. And in some cases, it's quite easy to grab data from other applications, such as DCS historians. There are more simulators and packages around than can be mastered in a lifetime. So getting the data into and out of simulators can be quite tedious and painstaking, which engineers detest. This tool provides an environment where you can find the results you need to run the plant safely, reliably, cost-effectively, and in an environmentally friendly manner. Doing these individual tasks takes time and is not always easy to do. Most of all, this tool provides a huge convenience to our SulfurPro and ProTreat users. But what's under the hood of this hot rod? At the root, there are VBA class objects that hook into or pass information to and from ProTreat and SulfurPro simulations via the COM objects. The code automatically inputs plant data into the simulators, runs the model, and retrieves the simulation output with custom VBA user-defined functions, such as stream results, unit operations output, and process advice. This slide is a bit busy visually, but represents the steps in the communications for retrieving a stream result from ProTreat and SulfurPro using a custom user-defined function. First, the user-defined function is queried by a user to fetch the ProTreat results. Next, Excel presents the dialog to fill in the arguments for the function. Next, the VBA function code transfers user data from a VBA class object in memory. The VBA class object procedure then passes the data for the COM instance of the simulator. The COM object then passes the results from the simulator back to the VBA class object. And finally, VBA passes the function results back to the cells in the spreadsheet to be viewed by the user. So, those are the basic steps for how the tool works. But how do you, as a user, even begin? First, the user event, hitting Control P, launches the subroutine showForm. The showForm then reveals the user form and instantiates the global ProTreat COM object. As the user enters data and selects controls, an event triggers a subroutine to build an Excel function, Text Builder, and a result value if the conditions are met to do so. The COM object instance is then sent data from VBA, which is then returned from ProTreat results file to VBA via the COM object. VBA then updates the form by a subroutine procedure. And finally, the function is pasted into Excel by VBA when the button is pressed to do so. So now we'll move on to the first case study example, showing how ProBot was used. The first example shows some of the safety aspects in a Klaus sulfur plant 2-zone reaction furnace, and how those are accounted for within the ProBot tool. Case study 1 is about a plant that had a safety issue that they didn't know about. The plant had complained about repetitive failures of the refractory in the front zone of their reaction furnace. The plant is a typical 3-bed Klaus unit with indirect HP steam reheat, a 2-pass waste heat boiler, and a 2-zone thermal reactor reaction furnace that is used for ammonia destruction. By varying the split of amine acid gas around the burner, the temperature in the front chamber, zone 1, of the furnace can be controlled for ammonia destruction. Ammonia destruction takes time, temperature, mixing, and SO2. SO2 partial pressure can also be controlled to some degree to assist in ammonia destruction with the zone split. The area where refractory failures are occurring was at the top half of the front zone. In OGT's experience, this can be a weak link in the armor of a sulfur plant. The keying of the brick around the head transition can be tricky to get right and requires an engineered solution. This is also the hottest area of the sulfur plant. OGT set up a monitoring system for this plant using ProBot technology that we will switch over to. The ProBot model looks like a spreadsheet, but is really much more. Feed compositions to the plant from a recent test run were loaded and are used by the tool. The compositions can be updated at any time either with the spreadsheet or from a remote data source, such as a refinery LP model or DCS data historian. Much of the plant information has been deliberately obscured to protect the identity of the plant. The plant model input sheet contains an area where the DCS data historian can be hooked into, as it is available. Input data fields are noted in blue font, formulas are in black. A dashboard at the top includes buttons to either load and save the model, or load, save, and run the model. DCS data can be given valid ranges for the data. In the event of the actual data falling outside of the valid range, a default override can be furnished. Data can be entered into any units that are currently supported by ProTreat and SulfurPro. For example, if we wanted to change the amine acid gas feed temperature from its present value of 120 degrees Fahrenheit to, say, 50 degrees Celsius, we could do this easily. So the basic idea here is that anytime the plant data change, or if a user wants to drive his or her model from Excel, the change is easy. If we click the Load and Save Model button, then the current values are loaded into the digital twin. We see a message box that the flowsheet was loaded and saved successfully. Flipping over to our plant model, we can look at the inlet block amine acid gas and TGU. Notice how the original 120 degree Fahrenheit temperature specification is still there. That is because our ProBot model loaded a separate copy of this flowsheet to work with in a hidden COM object. If we flip to the simulation results and back to the input, we can see how the 50 degrees Celsius temperature specification was accepted. If you were looking in the Windows Task Manager, you would find that there are two instances of SulfurPro model running. One that we are looking at, and the other that is the hidden COM object. The COM object is not visible, but present and active as long as the Excel spreadsheet is in memory. Okay, so coming back to our ProBot model, let's take a look at the output summary for the base case operations that were set up and obtained by ProBot. We have a summary of results where design data are loaded in so that you can quickly determine how loaded up the unit is. A summary of the sulfur balance and recovery across the plant is given. Several parameters are listed in red and show that for this plant, the sour water stripper gas flow rate and sulfur load to the TGU are exceeding their design values. While this can be common in plants, it points to areas where bottlenecks may be an issue. We can also see that for this plant, some advice feedback is given that the high water content of the feed may be limiting the plant capacity and that the normalized plant pressure drop is higher than design. The high DP may be a reflection of the excess water coming to the plant in the feeds. Focusing on the reaction furnace monitoring, there are several red flags. So the Zone 1 simulated temperature is above 2800 degrees Fahrenheit, which is higher than the refractory is rated for. Note that there is feedback given by the process advisor as well to calibrate TEIs in both the reaction furnace zones. So the virtual model provides a way to validate the field temperature measurements devices. We also see that there is advice to consider reducing the amount of clean amine acid gas bypassed to the back zone. That is helpful, but how much do we reduce it? It is easy enough to see this by making a move on the virtual model. We can do this right away as a sensitivity in the copy of the flowsheet that we were looking at. By opening up the zone split, we can change that value from 30 to 50% and then rerun the model to get the results. Looking at the results, we can see that the temperature is now just under 2600 degrees Fahrenheit leaving the front zone, which is a safer operating temperature. We can also check that the ammonia destruction is still acceptable by opening the Zone 2 furnace block, or by checking it in the spreadsheet here. So, if we were the plant engineers or operators, we can test out the waters in the virtual model before trying the move in the plant. Alternatively, the virtual model can be used as a training tool. This next example will look at a debottlenecking project for a TGU that was performed and how the plant saved hundreds of thousands of dollars by making one simple, at least on paper, move. Case Study 2 was generated from a recent troubleshooting effort that OGT conducted for a plant that was full on sulfur capacity. The hydraulic back pressure of the respective Klaus TGU system was being reached. The TGU regenerator steam flow rate was maxed out. The TGU system ProTreat model is shown here. The plant is a fairly typical reduction quench amine unit running MDEA. The front end uses a reducing gas generator to furnish hydrogen with supplemental hydrogen feed. The quench tower is a single pump around loop with a main and a trim cooler. We will take a look at a few of the details of the ProBot model for the amine section of the TGU. Starting with the solvent analysis, we can see that this is a 35 weight % nominal MDEA strength system, with a few thousand ppm by weight heath-stable salts. The amine is not just MDEA. There is just under 2 weight % DEA as well that showed up in the cation chromatographic analysis. It should be noted that the H2S lean loading was below the detectable limit, and the amount of H2S used in the simulation was found by charge balance, which is detailed at the bottom of the sheet. The visual characteristics of an amine sample, color, and clarity can provide some useful information about the amine system hygiene. ProBot includes a virtual visual sample bottle, which can be calibrated to an actual sample or a picture of a sample. For the current sample, note that the process advisor states the hydrocarbon levels appear to be low, and there are small microscopic iron or iron sulfide particles with some chelation. If the color of the leanamine had changed from the present yellow to moderately green, this can be simulated in our virtual sample, which has a color spectrum calibration for different treating surfaces. We will not change the clarity dimension, but this can be done as well with the horizontal adjustment slider. Notice how the process advice changes and states now that the particle filtration system should be evaluated. If we scroll down further in the solvent analysis report, we can see some additional parameters that are rolled into the charge balance and the analysis. The measured sample pH is in good agreement with the simulated pH using the measured concentrations of components in the solvent that are on this sheet. We have some basic model input next that involves the lean amine solvent rate, temperature, and pressure that comes from the DCS. Just like we saw with the Klaus example, data validation is used to condition out bad input data from the virtual plant model. Also included on this sheet are some basic parameters that can be used to roll the plant's current operating cost into the ProBot report. The absorber sheet shows a sketch of the system with inlet and outlet streams. A comparison of measured to simulated data is provided where available. Some useful plots to the right are included for the current operations. The comparison of actual to equilibrium H2S shows a pinch at the top of the column. This is referred to as a lean side pinch. A lean side pinch can only be relieved by reducing the lean loading of the solvent. Since we saw already that the lean loadings were quite low, this is a useful piece of information. Further out to the right, we can see what the predicted internal temperature is for the column. If your tower is fortunate enough to have internal thermocouple measurements, these can be compared versus the model to get a sense of how well the model agrees. Further down, we have a summary of how the column is performing compared to established system-specific limits. We also see a piece of advice for this plant to consider reducing circulation subject to treating specs and objectives. Notice how the column is nowhere near jet flood or downcomer flood. A little further down yet, material and energy balances around the column are reported. The agreement is within a few percent on the material balance and energy balance. The better these are in agreement, the more faith that we can place in the digital twins results. By tracking deviations in the material balance and energy balances over time, an indication can be made on when the next performance test may need to be scheduled, or it may be time to review instrument flow calibrations. Moving on to the Regenerator tab, we have a similarly laid out sketch with data comparison. For the sake of time, we will focus on the process advisor and what it has to say about the plant. There are several areas that the advisor flagged to take a look at. First, we can see that the system exceeded its design limits and is running beyond the design reboiler steam limit. It is also noted that the reboiler duty has room for optimization and that the column may be fouled or short of design capacity. Reflex flow has also exceeded the design limit. With this collective advice in mind, we can look at evaluating moves on the unit to relieve some of these limits. The first thing that came to mind to OGT in reviewing this data was whether the unit needed to be running so much circulation. Using the ProTreat model, we can create a side case study to evaluate dropping the circulation rate while keeping the steam rate where it is in the reboiler. For the sake of time, we've already created this case study, so I'll just show it opening up now to show how it was set up. You can see that we've taken the initial flow rate of 785 GPM and reduced it to 400 GPM in a series of 6 steps. Looking at the case study results, there is a sweet spot in the H2S treating from about 464 to 600 GPM. For a good part of this range, we're below 10 parts per million by volume H2S in the treating specification. So we could say drop the circulation rate to 500 GPM and still have plenty of cushion, where we could also consider a drop in the reboiler steam flow to lower the vapor traffic in the regenerator. We can also see where if we drop the solvent circulation, the TGU recycles less acid gas and is richer in H2S, about 5% rate. Because both of these outcomes open up room in plant capacity, they were considered worthy of trying in operations. The plant dropped rates successfully to 525 GPM without having to trigger a change authorization, which was worth several hundreds of thousands of dollars in sulfur capacity benefits. We will take one final look at the ProBot model output summary. As a reminder, this was for the pre-optimized operations. we can see some of the operating cost calculations, as well as the summary of the virtual corrosion coupon calculation results. By inputting the plant-specific objectives for service life, we can see how the predicted corrosion rates and service life estimates for different areas of the plants. A red flag on the hot lean amine piping exists in this plant, and expectations for 20 years of service life may be overly optimistic. Just in case you are wondering when this tool will become available, there are still some logistical challenges in place. First, we need to do a beta stress test, which is currently in progress with several operating companies. The feedback that we get from this test is extremely important to establish use cases and to root out any bugs that may be present. After all, this is still a piece of software, and although it's a sensitive topic for a software company, software in and of itself will never ever be 100% bug free. We anticipate that the tool will be released to the general public with the newest versions of ProTreat and SulForPro later this year. With that, I'd like to once again thank the SulGas Committee and open the floor to any questions that you might have at this time. Thank you.